All right, in this video, I'm gonna go over how front splitters work on cars. I kind of broke it up into 3 sections. So the first one is a splitter length. So how does that affect the splitter's performance? The second one is a splitter's thickness or relative height to the ground. How does that affect its performance? And lastly is a splitter shape. I have at least one way where all of these affect the performance. Chances are I'm missing some things though, but I looked around at a couple videos beforehand, got some ideas, and this video is kind of grouping them all together and talking about stuff that they didn't talk about in the videos. Yeah. Okay, so let's start with number 1, the splitter length. So how does a splitter length affect it? So in order to understand that, I'm on the eraser. All right, so we've got our air coming relatively towards the car. And what happens when it hits the car? It hits and it stops. It doesn't have any more relative velocity. Instead, because of the Bernoulli equation, all of that velocity gets turned into pressure. And as a result, you have a pressure spike at the front of the car. And that's part of the reason why frontal area causes drag. Is because if you have a lot of frontal area, you're gonna have a lot of high pressure, and all of this high pressure is pushing against the car. You don't really see those arrows, but it's pushing against the car, pushing the car backwards. But anyways, you have this high pressure air buildup at the front of the car because of the stagnation pressure. This air can technically go in only 4 directions, but I'm going to assume it only goes in 2 directions. I'm going to assume it either goes above the car or below the car. If it goes above the car, that's great. That's really great because now this high pressure air is pushing down on the car, producing downforce. But it also goes underneath the car, and that pushes up on the bottom of the car, and that produces lift. So it kind of counteracts itself. So why do we add a front splitter? Well, I kind of explained it such that it would lead into an intuitive answer. So let's see how intuitive it is. So you got your front splitter. Now it stops the high pressure stagnated air from being able to go underneath the car and produce lift. Instead, all of that high pressure stagnated air has to go above the car, and now it's kind of doubling down because now there's like twice as much air above the car producing downforce. So now you've got double downforce and no lift. So it's like quadruple the effect of not having a splitter basically. But anyways, the first reason that you have a splitter is because it stops this high pressure stagnation air from going underneath the car and producing lift. Now, why does a splitter length matter? Well, if you have let's start out with a short front splitter. If you have a short front splitter, like it ends right there, it's high pressure air, it could go around that front splitter and it'll still produce lift. That's a terrible arrow. It's a better arrow. But if you have a longer front splitter, it'll try to go forward, but it'll get stuck at some point because the free stream air is pushing back on it. And yeah, so CFD analysis is done on this sort of stuff to find the optimal length, because you don't want too short of a front splitter, because if you have too short of a front splitter, the air can go around it and go underneath it and lift up the car. And if you have too long of a front splitter, you'll scrape it more than necessary, which is not good. So that's kind of how splitter length affects splitter performance. Okay, number 2, splitter thickness and height. Okay, so let's say you've got a very thick splitter. So the oncoming air, let's say it hits the midpoint of this front splitter, and let's assume, I don't know if we should assume half of it goes above and half of it goes below, but let's assume that. So half of it goes above, half of it goes below, and it's rammed. The part that goes below is rammed from a volume with a height of this, so H1, to a volume with a height of this, H2. And H2 is way less than H1. So that means volume 2 is way less than volume 1. And in order to keep the mass flow rate the same, since, what is it? Q equals, I'm going to use m dot, equals density times velocity times cross-sectional area. And h, the height, is directly impacting the cross-sectional area. This is h, I don't want to call it length, I'll call it depth. So height times depth is cross-sectional area. Yeah, so if you're ramming all of this air from H1 down into H2, in order to keep the mass flow rate the same, density is not going to change. So velocity would have to increase. And higher velocity, going back to Bernoulli, higher velocity means lower pressure. So the more we can ram this air down into a smaller area, the higher velocity that the air underneath the car will be moving at. And if it's the higher velocity that the air is moving at underneath the car, the lower the pressure. And that's because of the Bernoulli equation. And lower pressure means downforce. So that's why you want either a really thick front splitter or be as close to the ground as possible. To illustrate that, again, I'll assume on the eraser. I'll assume we have a super thin front splitter. So again, we've got our air coming at the front splitter. Part of it goes above, part of it goes below. But now the part that goes below, it goes from this H1 to this H2. And they're not as drastically different. H1 and H2 are not as drastically different as they were with a super thick front splitter that was really low to the ground. As a result, the velocity increase will not be as much as with the super thick front splitter. And as a result, the pressure decrease will not be as much. And as a result, the downforce will not be as much as with a super thick front splitter that's really close to the ground. So that is pretty much point 2, splitter thickness and height. So ideally, you want height, you want the height between the splitter and the ground to be as low as possible. And with length, you want it to be as long as possible to prevent the stagnation air from going around it and underneath the car and producing lift. Point 3, splitter shape. All right. A lot of people, and for good reason, because it's cheap, they just use rectangular front splitters. So the front is rectangular. The front is not rounded or wing shape or anything. It's just rectangular. And that does accomplish both of these effects that we just talked about, point 1 and point 2. That still accomplishes both of those, but it will increase the drag associated with the front splitter, which is not good. And the reason for that, so you've got your oncoming air. And in aerodynamics, kind of a rule of thumb is wherever there's a sharp edge, it causes delamination. And delamination causes drag, excess drag. And I'll explain that. So you got the oncoming air, hits the front splitter right in the middle. And part of it goes above, part of it goes below. And instead of smoothly flowing over it, it's a sharp edge. So once it gets down to here, right at the corner, it can't change directions smoothly quickly. And sharp edges force it to do that, and it can't do that. So instead, what'll happen is it'll look like that. And there's going to be a gap here. And that gap, it's not going to be filled with nothing. It's going to be filled with turbulent air. And turbulent air sucks because turbulent air has a much higher drag coefficient than laminar air. And I'll explain that a bit. So, if you have laminar air, well, okay. I don't know how much I want to explain this, but basically the reason is, I'm assuming you already know engineering stuff. You got the no-slip condition, so the velocity of the air on a surface is not moving. And laminar air means the velocity would slowly increase. But if it's turbulent air, the velocity would increase rapidly. This is, how should I draw this plot? So this is height, and this is velocity. So once you've moved a tiny bit down, your velocity is insanely high already. Versus if it's a laminar, the line would look like that more. So if you move a tiny bit down, the velocity will not be as high as if it's turbulent. Turbulent laminar. Hopefully that made sense. And the way, I don't want to erase that yet. The way that friction is calculated has to do with the slope of literally the lines I just drew right at the 0 point. So right there, right there. And the turbulent air has a much steeper slope than the laminar air. And that's why it produces more drag, more skin friction drag. You know, I'm going to leave that there. Yeah. So instead of having sharp edges that cause delamination and turbulence, which causes higher drag, I should erase that. You want a nice airfoil shape. It doesn't have to be airfoil. It could be rounded at the front. Could be pointed up like that if you want. Literally, whatever it is. I mean, this still has sharp edges, so there's still going to be delamination, but the point is you don't want sharp edges. So I'm just going to draw an airfoil. So that way it's producing downforce because it's going to create a low pressure down here that interacts with the ground and pulls the ground up relative to the airfoil because of that low pressure zone. So splitter shape, you don't want it to be a rectangle because that causes higher drag because of the skin friction. Instead, you want it to be like an airfoil or like a rounded shape because it's much easier for the air to flow smoothly over a surface like this than it is for it to flow smoothly over a rectangular surface, because it can't over a rectangular surface because it can't change directions like that. It just can't do it. So instead, like I mentioned, what will happen is it'll glance off of here and then just go that way, and then you're left with turbulent air in here, and that's what you care about because that's what's touching the surface. Okay. I guess overall summary, splitter length, you want it to be as long as possible to stop stagnation air from going underneath the car and producing lift. Splitter thickness and or height, you want it to be as low to the ground as possible, such that this height ratio is as large as possible, such that the velocity ratio is as high as possible, such that the pressure ratio is as high as possible because of the Bernoulli. And lastly, you want it to be a smooth airfoil shape because if it's rectangular, it'll cause delamination, which causes higher drag. And if it's smooth, there's going to be less delamination and much lower drag. But luckily, all three of these things are kind of independent of each other. So you can kind of optimize all three of them at the same time. There's very little cost associated with improving any one of them relative to the other. But yeah, that is about it.